Okay, we'll go ahead and get started. So thanks everyone for joining our webinar, The Future of Physical AI, Introducing Adaptive World Models. For those of you who are new to Archetype, we're building intelligence for the physical world with AI that can interpret, reason, and act in the real world based on sensor data. My name is Aristo Chang, and I'm on the product marketing team at Archetype. And we are excited today to have our co-founder and chief scientist, Jaime Lien, here to walk us through the latest work and research on adaptive world models. We have a new position paper that we'll be releasing today, and we're excited to share a preview of that on this webinar. But before we hop into it, we'll just cover a couple housekeeping items. So the first point is that we are recording the session, so we will share a version of this after the call through email. And two, we're taking questions. So as any questions come up, please feel free to submit them. There is a Q&A feature in Zoom webinar that you can use to submit any questions. And we also want to note that there is also a chat feature as well, but we will not be monitoring that. So please use that Q&A button. Great. And so just for a quick lineup of the discussion today, we'll start with the presentation on adaptive world models. We'll then move into a demonstration of it and then end with that live Q&A. And so for this, we'll hear from our co-founder, chief scientist, Jaime, who heads up our research on Newton and adaptive world models. And we'll also hear from Marta, who's our creative technologist, and she'll provide a demonstration on what this actually looks like in practice. And then, of course, you know me, I'll be hosting the session. So with that, I will pass this on to Jaime.
Thanks, Aristo. I will share my screen. All right, thanks everybody for joining. I'm really excited to talk today about our work in adaptive world models and answer any questions that people might have about this work. As Aristo mentioned, our company is focused on building AI for the physical world. And what we see is that physical industries make up a huge percentage of our global economic activity. Industries like manufacturing, energy, logistics, and shipping, all of these run on the physical world and run on big physical complex systems. And despite all of that, what we've seen is that modern AI hasn't been able to fulfill many of the needs that these physical industries have. And specifically, we see that this intelligence gap for operating modern machinery is ever increasing, and the gap between the complexity of these systems and the available human intelligence to monitor and understand and operate them is just growing rapidly. This is due in large part to things like a shrinking availability of expert workforce. We see across almost every industrial sector that experienced operators are retiring. There are fewer people who are willing to dedicate the years, in many cases, in order to understand these machines. And all the while, the complexity of these systems is just increasing, both in terms of the scale of the systems and their interconnectivity across many different systems. And so what we're trying to address is this gap between the required system complexity and the available expertise that humans can provide. And what I would like to emphasize is that this problem of understanding physical systems, physical machinery, physical processes, is not a new problem. People have been trying to address this for over half a century. What we've seen is that all the way from the mid 1900s, when people started working on systems theory, control theory, all the way to present day, where we've gone through iterations of hybrid and switching systems, statistical types of control and fault detection, to more data-driven types of models, and then to today, things like physics-informed modeling. Many different approaches and attempts to solve this basic problem of how do you actually understand the way that a physical system behaves and operates. And across all of them, the main limitations that we've seen is that they're all bounded by the domain knowledge that you have to bring in a priori in order to understand the machine. What that means is that the physical structure of these processes and these operations basically has to be understood and specified in advance, at least to a partial degree, in order to build these models. And because of that, building these models requires a lot of domain expertise. It requires a lot of system-specific engineering for each deployment. And basically, the model is only capturing what humans have already understood about these machines and these processes. The understanding is bounded by what humans anticipate a priori. So because of this, these solutions fundamentally are unable to scale across the very wide diversity of physical processes and different machines that we see in physical industries today. Um, when we move to modern AI, what we have observed is that the field is in general converging around this idea of world models. But in general, they're not addressing the same problem that we are trying to solve in the physical world. Um, so these world models that other people are building and the paradigms that they've constructed around them are largely around predicting how environments and physical spaces evolve over time. So can you take observations of what is happening now and predict what is going to happen next? And the applications of these largely are around things like simulating 3D environments, producing synthetic data for training robotics or autonomous machines. There's work like JEPA around predictive representation models, largely to do things like learn optimal actions that robotic systems can take. And of course, a paradigm around reinforcement learned world models, which is basically around task-specific training of robots and agents in order to navigate these systems. So the common paradigm across all of these is that they're largely around generating or predicting what's going to happen in the future. The paradigm that we see a need for and are basing our work around is understanding the current state of the system, how it got to that current state, and from that current state, what is likely to happen next. So it's more of an epistemic reasoning about the operational structure of machines and physical processes, rather than just a prediction of what the signal or the space is going to look like at a future time. So in general, we see that the space of world models that other people have designed and the approaches that they're taking doesn't fulfill the needs of this physical and operational understanding that we see the need for. And in parallel, these other techniques that ML and AI have produced in order to address these physical problems haven't been able to solve the problem either compared to classical techniques. Fundamentally, the reason why is because of this very large diversity and non-stationarity of the physical world. So unlike text, for example, in the physical world, you may have a nominal design of an asset or a machine, but every instantiation of that design actually differs quite a bit. There are small differences in the hardware, there are differences in the configuration of the machine. So there's a uniqueness, even if the nominal type of the machine is the same. In parallel, you have the deployment environment and the environmental characteristics and perturbations that they introduce onto the process actually cause wildly divergent behaviors of machines that are deployed even with the same nominal type, but in different places or different times. And so you see things like load variations or the ambient conditions having a very large role in defining the overall operational behavior of a machine. Similarly, just over time, machines change. They experience wear and tear, they experience degradation, changes in the environmental factors evolve. And so all of this means that the entire process is ever changing. And finally, we have this case where a lot of critical events, and especially safety critical events, might actually never be captured or recorded in a pre-existing training data set at all. These are things like novel states of a machine, failures that happen, very, very irregularly, and a lot of novel transition states. And all of these taken together means that any static global training corpus isn't able to keep up with the reality of the way that the physical world and these physical systems are behaving. So the relevant operational structure of these machines is specifically tied to each local deployment. It's always changing in time, and it can't be captured by one global static training data set. We believe that this is a limitation not of data, The observations are there, and especially what we saw with IoT, for example, 10, 15 years ago, is that there's a huge preponderance of sensors already embedded in these systems or in the environment. And so with modern machinery today, we see that every machine actually is continuously monitoring its internal state, a lot of factors of the external environmental conditions. And so the preponderance of all of these sensor observations basically means that each machine already has an effective perception system. It has an observation of its local universe. What is missing and where that gap comes in is actually architectural, that there needs to be the ability for these world models to adapt to these local observations in a self-supervised and autonomous way. And that's how we can get across and overcome the scaling limitation, where we've seen classical techniques fail because they require this per system human engineering effort. So what we are focused on and what we're presenting today is basically a new paradigm for world models that we call adaptive world models. What we mean by this is world models that are able to autonomously discover directly through sensor observation, so without extensive human per system engineering, to discover each machine's unique operational ontology. And when we say operational ontology, we mean the way that the system behaves, its different operating regimes, the way that it transitions between these operating regimes, its overall dynamics, that these things can be discovered, essentially the machine native language of how these systems behave can be learned through self-supervised means and continuously adapt to changes in the physical world and in behavior in a way that doesn't require humans to go in and manually teach the machine how to do this. And so the overall flow of this is basically that we can take these local observations that each machine is collecting and monitoring of its internal conditions, its local environment. We apply a universal foundation model, which provides the representational substrate that's common across all of these machines, and then build on top of that an adaptive learning mechanism, which allows that representation to be grounded in the specific machine physics and its operating context and its history. That forms this machine native understanding of the behavior of that system. And then we introduce a human language interface so that this machine native world model, this understanding, can be translated into natural language that then allows the machine to explain to a human operator what it understands about the system and also allow collaboration and interaction between both the AI and the human. I mentioned in the previous slide that this adaptive local world model architecture, one of the key ingredients of it is that we have this foundational representation layer. We published this work back in the end of 2024. Essentially, what this representation layer does is that it's able to take diverse multimodal sensor observations, so continuous streams of different physical measurements of the system, and represent them in a common mathematical space, what we call a latent representation, in a way that retains a lot of the structure and the physical phenomena that's common across all of these different systems, sensors, and domains. And essentially, this latent representation, this mathematical space, is what allows us to then discover these machine-specific operating regimes and dynamics in one common way. So from within that representation space, we can actually build this structured understanding, very analogous to the way that a human forms a mental model after many years of direct experience with the machine. Our AI is able to develop this understanding, a structured internal model of the different behaviors that the system has. And this is represented conceptually as a set of discrete operating regimes that the machine transitions between. And what the model can do is adapt to the specifics of that machine, what each regime corresponds to in terms of direct measurements, and then how it transitions from one state to the other. And then finally, as I mentioned, the translation of these machine-discovered states from the data can be turned into natural language descriptors And this basically enables the human aspect of accessibility and interaction and collaboration with AI in order to both transfer the knowledge from the machine to the human, but also for the human to prompt and guide the machine to provide the understanding, recommendations, or actions that it wants. And so these three components, the foundational layer of representation, the structured mental model or internal model of the specific machine dynamics, the operational behavior of the machine, and then the translation to human language, compose the three main architectural blocks of this adaptive world model paradigm. Because of this, we can now provide some key attributes to our customers in terms of what an adaptive world model can do and properties that it can provide in order to fulfill specific needs and use cases that they have. Obviously, that these adaptive world models are grounded in physical reality and not only global reality, but specific reality of each deployment of a specific machine. This understanding is discrete and referenceable. So unlike just a continuous embedding space or a mathematical space, you can actually point to a specific discrete state of the system, say that the system is in that state, and also refer to the states that it went through in order to get there. This epistemic operational understanding also supports things like downstream, more complex reasoning, why it reached the state that it went into. It's communicable because of the discreteness and referenceability. We can impose things like epistemic uncertainty, not only in representing a level of confidence about what state it's in, but also able to represent when it has discovered something that is new. So something anomalous that wasn't captured in a predefined model of the system behavior. And finally, that it's scalable and generalizable. So because of this foundation model that it's built on top of and the common adaptation mechanism, it means that we can then scale to any sort of physical process or any sort of physical system without this per machine type of engineering. So I'll pause here for Marta to show a live demo, which is, I think, probably the best illustration of what we mean in concrete terms.
Thank you, Jaime. Hi, everyone. Here I'll share with you a demo that we've built to showcase this idea of the adaptive world model. In this demo, we are building this, what we call the operational state monitoring agent, which is this AI that works with this adaptive world model under the hood. And this model understands the behavior of machines directly from sensor data. So it should be able to extract their states, their rhythms, their failures. So for this, we will start by providing a few data sets. So I'll upload a couple of data sets from some HVAC machines. These files include data from the past couple of months of both normal regimes and also some faulty behaviors. Then I will run it through our model, and we will start extracting these patterns. There is like no labels and no annotations in these files. There is just what the machine produces while it operates. Here we're seeing how the windows are coming in. And here we are starting to see the representation. It's running a little bit slow. So what we are seeing right now is how Newton builds its understanding of the world. The model is encoding every moment of operation into a latent space. That is what Jaime was talking about. So each pattern, like each data point, is getting represented into this embedding space, and it's being projected. So what we are seeing is this projection of the latent space, where similar behaviors will be close together and different behaviors will drift apart. I'm gonna just do a small test here because we are running this demo live, and I don't know if I'm getting like some issues with the internet connection. I'm getting like some latency problems. Okay, here we see this projection of the latent space. Each cluster is a distinct regime Newton has discovered on its own across all the HVAC units. It's like we can think about it as the agent's internal map of how these machines work. So from here, we can say, let's teach the agent our vocabulary. So let's say that we can identify some points as normal behavior. So I will just label them. But then I will see that there's like some other clusters that emerge that I cannot really identify. So I will provide some labeled examples to the machine. So I'll provide like these labeled examples that will anchor the language labels to these clusters that have been self-discovered. So as we see, the first example has been like mapped into this area. So we see the water side coming up here. And now this other valve stack probably will like lighten up there. And yeah, in here, like what we are seeing is like the internal map of how these machines are working. Let's see. All right, so now it came up. You see how the cool valve stack like appeared here. So this embedding, so some of these data points were mapped into this latent space. What we are gonna do now is testing it with our data file. So we will set up like a sensor stream from an HVAC machine, and we will start to analyze it with a classifier. What we are seeing here is live sensor data coming in, and then the agent classifying every point as an embedding. So we see here how this sensor data is being projected into the embedding space, and it's landing into these different points. Then we can like visualize how Newton like perceives and detects these different states, and also like adds this language layer that extracts the insights and turns it into accessible data to the operators. We see how like different states come in. We can start like evaluating the transitions, and we can start like understanding this map from our machine, and yeah, we can see how it's like from a non-labeled and no-annotated set of data. We can start to understand its internal structure that Jamie was talking about, and we can start like understanding patterns and behaviors. Thank you, Jamie. Over to you.
Thanks, Marta. Take over sharing my screen again. So Marta gave a really nice and compelling demonstration of what the adaptive world model can provide in terms of understanding of a specific system. I'd like to take the opportunity now to describe a little more detail about the underlying technical details of the underlying models and the learning paradigms. So as I discussed in the earlier part of the talk, and what Marta was showing is basically that the adaptive world model is built on top of this foundation physical world model, which is essentially a learned mathematical representation that generalizes across all different types of physical sensor modalities and physical domains in order to provide a latent representation of physical processes. So essentially what we did in order to develop this foundation model is that we trained from a very sparse but diverse set of physical measurements. And these included, very diverse types of physical quantities like electrical quantities, mineralogical quantities, different types of gas and environmental type of quantities. And what we fundamentally wanted to show, and our core hypothesis, is that from the sparse but diverse set of observations, the model can learn some common underlying structure of physical phenomena that can then allow it to understand phenomena and sensor observations that it has never been trained on. And this ability to generalize beyond the specific observations that it saw in the training data set, we see as evidence that it has learned something more fundamental than just the sensor traces themselves, that there's some common underlying processes that are shared across different physical phenomena. And so fundamentally, this model is a transformer-based backbone that takes in multivariate, so many different sensor streams simultaneously. And then it maps them into this latent embedding space. The training of this embedding representation is basically done, as I mentioned, on this very general cross-modal, cross-domain corpus of data, but more importantly, it's done in a totally self-supervised way. So we did not inject any sort of, like human physical equations. We didn't inject any labels or any sort of textual description of what the data represented. We merely let the model learn on its own from the data what these common underlying structures of physical processes would be. And the outcome of all of this is that we arrived at this latent representation that we could then apply to downstream tasks and show that the performance across those tasks was in almost all cases better than what you would get from training on the target data set alone. So what we mean by this is that we have our pre-trained foundation model. We compare its performance to, let's say, a model trained specifically on a transformer data set. And then we compare the performance of our pre-trained model to the model that had been trained on that data set. And so here's one example of results that we got, looking at the ability of the different models in order to predict the trajectory of these physical processes over time. So forecasting the future behavior of these processes. And we looked across diverse types of complex real-world processes like electrical consumption, different weather parameters, the oil temperature of an electrical transformer. And what we're showing here is basically the mean square error of our model in blue compared to the mean square error of forecasting to a model that had been trained only on that specific data. And in all of these cases, what we saw is that our model actually outperformed these narrow domain-specific, sensor-specific models, which is echoing a lot of the phenomena that we've seen with, for example, LLMs today, where if you train on this broad, diverse corpus of data, in many cases, the model can outperform a model that has only been trained on this very specific domain. So speaking to the ability of models to learn and transfer knowledge from one domain to another within one single large capacity model. As I mentioned, the crux of this model, of course, it can be applied to these downstream tasks, but the real structure and inherent learned properties of the model are captured in this latent embedding space. And these are some examples that we observed of showing how this latent representation captures structure that generalizes across these different diverse types of physical systems, machines, and sensors. So in these examples, we took our frozen pre-trained embedding model, and then we applied the sensor data from three very different physical systems. So the gearbox inside a motor, an industrial pump, an oil and gas drilling rig. In all of these cases, the sensors equipping these different machines are wildly diverse. In many cases, they're very specific to that particular industry, that domain, that machine. And we actually have relatively little contextual information about what those exact sensors are. But our model is able to take that sensor data and map it into this common mathematical latent space. And once that data is mapped into this space, what we see is that there's an emergent structure that appears because of the way that the latent space, the geometry of the latent space. So in the case of the motor, for example, if we take these sensor traces, these sensor measurements, we actually see groupings of the measurements according to whether the gearbox was healthy or it had a broken tooth. Or in the case of the industrial pump, we can actually see the trajectory of the pump going from a normal state to a state where it had a blocked intake. Or for the oil and gas drilling rig, we can actually see distinct clusters corresponding to all the different states that a drilling rig goes through over the course of a drilling session. So circulating, drilling, rotating, slipping, all of these are actually captured in terms of specific geometric structures within this pre-trained latent space. And so when we talk about the discovery of the operational ontology, what we mean is that within this latent space, we can actually form these discrete groupings of observations that correspond to very specific and discrete operating states of the system. So the groupings themselves form a discrete vocabulary of the different ways that the system behaves. And we can, assign a human interpretable name to them through this natural language interface. So now we can talk about the motor, not just in terms of continuous sensor observations, but whether the state of the motor is healthy or it's anomalous. Or we can talk about, whether the industrial pump, not just the morphological features of the sensor data, but also that it's transitioning from one state to the other. And so we call this an ontology because it basically is a structured understanding of the way that the machine is behaving, how it got to its current state, and the states that will happen next. When we talk about the architecture that can form the structured understanding, this is a very high-level block diagram of what that architecture looks like. So as I mentioned, we have these diverse sensor observations represented as time-varying quantities that are fed into one common foundation encoder. This is a universal and pre-trained encoder, so a component of the model that is common across all of these different systems and captures some commonality in underlying physical behavior that generalizes across these diverse systems. And then the structure that's formed on top of that common continuous representation, I think Marta referred to it as a map, which is a nice way to think of it conceptually, that you have this landscape and then we can learn and adapt the map of that landscape, and so that we can refer to specific parts of it with discrete names. And we call that the concept former. So it's basically assigning discrete names to regions of this landscape that correspond to specific operating states of the machine. We can learn this and adapt it in tandem with a model of how these concepts or different operating regimes transition from one to the other. So the concept former and the concept sequence model together form what we call this operational ontology of the specific machine's behavior. And that learning is grounded in the specific sensor observation that the machine is making. And because it's learned from data itself, from observation, it means that this learning can happen continuously and adaptively without human need for a lot of per domain and per machine type of engineering. I wanted to mention that there are additional techniques that we both have built, but also are providing to our customers in terms of making these models specific for their particular problems, their particular physical systems, and their particular deployments. So one of these techniques is fine tuning. This is where we can take relatively small amounts of labeled data and actually modify the weights of the model so that it is fine-tuned, specialized for our customers' particular domain and applications. The other technique that we have productized and are offering is in-context learning. So this is something that Marta mentioned as well in her demo, the ability to provide some examples of data and labels, not for changing the model weights, but purely as examples within the context window. And so that provides a very lightweight way and mechanism to steer the model to do and to recognize the sort of states or operations or phenomena that are of interest for a particular customer. This is just a conceptual graphical representation of what these different stages of the overall architecture looks like. So at the output of our pre-trained model, we have these continuous latent vectors. These are the representations of the sensor data within this common mathematical space, the discretization into different concepts which correspond to the operating regimes, and then kind of a conceptual view of the internal mental model that the model forms of the different transition dynamics between the regimes. I'll provide and talk through a quick example of the fine-tuning service that we're providing to our customers as a way to show concretely how a customer might use our platform, our core product, in order to modify and adapt our foundation model and the surrounding AI infrastructure for their particular use cases. So in this example, we're showing the console, which is basically the UI to our platform. And we're using this fine-tuning service, which is provided as a discrete job that a customer might do in order to adapt the model for their particular use case. So you can see in that example, through this graphical user face, the user is able to specify the base model that they want to use, apply their choice of the suffix to indicate what the name of the fine-tuned model will be, and then upload the specific training data that they want to use for fine-tuning the data, for fine-tuning the model. They can also upload this validation data set, which is used to measure the performance on data that is outside of the training set. And so what we provide within our console is basically ways to monitor and view graphically the progress of this fine-tuning job. So you can see, for example, how the loss evolves over time with each iteration step of the fine-tuning process. There are logs which allow visibility into what stage of the fine-tuning is at. And then finally, a viewpoint into the different checkpoints that emerge from this fine-tuning process that represent different instantiations of the model as it goes through this process. And at the output of that, basically the customer will have their own, their own specific version of the model that they can then apply, trained on their proprietary data in many cases, but that is specific and specialized for their particular domains, their particular machines and processes, and their particular use cases. Here's one concrete example of a use case that we've looked into, both on our end internally as a vehicle for understanding the performance of our model, but also through real-world customer use cases that we have worked with. And so in this use case, we're looking into the operational state of an oil and gas drilling rig over the course of drilling sessions. So basically, these rigs go through numerous transitions of different operating states over the course of days to weeks of a drilling session. One of the key difficulties here is that each drilling rig, depending on where it's deployed, its specific hardware configuration, the terrain that it's drilling in, will have slightly different behavior and operating characteristics, which is this non-stationarity and diversity that we talked about as a fundamental challenge of physical systems. And so what they're fundamentally interested in is the ability to not have to do this site-specific model training or model development, and really trying to cut down the development time of deploying this sort of intelligence across very broad and diverse deployment sites, different hardware configurations, different instantiations of the nominal design. And so what they're trying to do here is basically continuously monitor what the state of the oil and gas drilling rig is with minimal amounts of label data, so that they can make sure that the oil and gas drilling rig is staying within nominal operational bounds and not drifting towards something that would cause a loss in productivity, or other safety critical type of regimes. And so this is a visualization basically of how our model would work with this data. We can take the raw sensor data from these oil and gas drilling rigs. In many cases, they have sensors both at the surface where the torque is actually applied, as well as the downhole drilling head. And you can see from this example open source data set that is pretty representative of these sort of systems, that the sensor data itself is very complex. It's not it doesn't have very canonical type of morphological features. It's noisy, and so it's very representative of real world data. When we apply our model to this data, we can see that now a structure emerges where you can actually group together different clusters of these observations within this mathematical space, even though the model has never seen before, of course, this particular domain or even these particular sensors. And then once that structure of the operational regimes emerges, then it becomes very straightforward to take a few labeled examples in order to apply a human interpretable name to each of those clusters. And now we can continuously identify with streaming input data, whether the drill is drilling or tripping, circulating, or going through any number of different operational states. So I'll close it out here. Happy to answer any questions about the overall work or future directions that we're going into, as well as the underlying concepts.
Great. Thanks so much, Jamie. So I've been monitoring the questions. We'll try to get through as many as we can. I know we only have a few minutes left, but let's start with I'll kind of go up and down between these so we get some from the beginning and the end. Let's start with this one. There's a question around how should we think about this? Should we think about it as like a modern AI take on dynamic clustering or unsupervised learning? Like, how can we think about adaptive world models in that context?
Yeah, I would say I wouldn't say it's like a modern take, but I think there are some common underlying techniques. Certainly, like clustering is something that is a broad technique, but I think fundamentally what we're advocating for and what we're aiming for is that the foundation model itself, the representation model, means that when you actually apply these techniques, that the emergent groupings or clusters actually correspond to something physically meaningful. So it's less about the technique itself, and it's what the technique applied to our foundation model can result in. And what we see is that it actually results in physically meaningful operating regimes. And so it allows for the discovery of these operational states and transition dynamics from this latent space alone. So it's less about the specific technique that's used, and I'll say we have many different specific techniques and flavors of techniques that we're investigating, but fundamentally the core concept and hypothesis of it is that the emergent structure of the latent representation itself means that when you apply these techniques, the result is something that is operationally relevant to these specific physical processes.
Great, thank you. And here's one too. Does the foundation encoder only take one-dimensional time series, or can we think about, or can we take any parameter set? Uh, as an example, voltage versus current.
Yeah, currently it takes in multivariate data. So we can take in, diverse types of streams, either multiple voltage streams, as an example, or voltage, current, diverse types of physical quantities themselves. We are continuing to improve and evolve the way that these different multivariate streams of data are encoded within the representation model. But yes, at the input layer, it can take in not just one stream, but multiple.
Great, thank you. Um, and let's see, there's one here. Here's a question. Curious, this may depend on use case, but curious if we run into situations of oversaturation or overfitting on raw sensor data. And is there a point where, too much data becomes a distraction, or where some data, while small in quantity, is more valuable than others?
Yeah, that's a really good question. Um, I think this is one of the benefits of using a foundation model as the base layer, in that it's trained, you know, across this very broad set and diverse set of data. So the foundation model itself, we haven't seen signs of overfitting on, simply because in all of these cases, it wasn't actually trained on the target data itself. I think where that question comes into play is at the adaptive layer. And so this is something that we are actively looking into, like how much data is actually appropriate for adaptation. I think it's a question that we're still looking into for an optimal answer. But I will say that I think this is exactly one of the reasons why adaptation is so critical. Because if you have just a static model, you have no way to recover from these cases of overfitting or the model underperforming. And unless you actually go in and provide more labeled data or a lot of human engineering effort involved, the ability to adapt in a self-supervised manner means that there is a possibility of recovering from these cases where the initial model that emerges is suboptimal. And so we really see the underlying paradigm of self-supervised adaptation as critical for addressing these kinds of failure points.
Great. Thanks so much, Jamie. We are at time a little over, but there's one thing I'll just answer quickly. I see there's a question around once the space is mapped, can this run as a real-time system uh, on the edge or cloud only? And I'll just make a quick comment here that yes, we can. And we do deploy in situations that are in the edge, on premise, and in the cloud. Um, Yeah, I think that's all the time we have for today. Thank you so much for the participation and lots of great questions here. Jamie, do you mind just clicking forward one slide? Great. And so, as a reminder, we will be sharing a recording of this session through email, but please connect with us on LinkedIn, on X, on our website. Stay up to date. We do a lot of these webinars quite frequently, so follow us to stay up to date on the next one. And thanks so much again, Jamie, for coming and presenting on adaptive world models. And thank you, Marta, for the great demonstration. And appreciate everyone for joining and having such an engaging session today.
Thank you.